We are starting this chapter off talking about molecular geometry. I always like this chapter. It's a little bit of a break from some of the things we've been doing with some of the math, and I just find it kind of interesting visually. Okay, so the first thing we're going to look at today, spending most of the time, is, again, this is probably something you remember a little bit from last year, maybe, the Vesper model or theory. So what we're looking at here, what this stands for is valence shell, electrons, pair, repulsion model. So how does the shape of the molecule look based on the number of valence shell electrons that it has? And we'll look at many examples going through here. So one of the ways you can have this conversation or look at the molecule itself is looking at the electron domains. And what that refers to is an area where electrons are found. And that's a little bit vague, and that's okay, that's good. So an area where electrons are found. What would those areas be, or what could they be? Well, they could be a region. Well, a region could be bonded to another atom, or just like a lone pair, non-bonding. So they could just be hanging out there, or they could be the electrons that are between two atoms. Furthermore, that electron domain could be, and again, it could be non-bonding, just hanging out there, but if it's bonded, it could be a single, double, or a triple bond. So we don't distinguish between, like, well, what kind of a bond is it? It doesn't matter. If it's a place where electrons are found, that's the whole conversation. A place where electrons are found. We're not necessarily concerned about what they're doing. They're there. Okay. Something else we can refer to is the electron domain geometry. So, clarifying, what is the shape of the structure just and only looking at the electron domains? So I'm looking as if I can see the electrons out there. So I look at these different electron domains, and based on that, what is the shape? Now, a different conversation, this is probably the one we have more so, is the molecular domain geometry. And with that, again, what does the molecule look like based on the electron domain geometry? So based on electron domain geometry, what does the molecule look like? Okay, so we're going to have lots of these little examples here. I'll give these headings, and leave yourself as much space as you want, but you'll continue on to different pages. So I'll write one heading. I'll write this route, electron domains. Underline that. Based on that, the geometry. How many bonds are hanging out there? How many non-bonding pairs are out there. And then the molecular geometry. There's one more thing, I want to say Vesper, that's not the right words to use. The name's escaping me. The hybrids, the hybrid model. I'll come back to that later on. We're not going to do that right now. Okay. So I'm going to kind of switch back and forth here where there's another site, which is really good, and you definitely should use it. But I'll kind of put some numbers down, and then we'll go over and talk, and we'll just keep bouncing back and forth. So the first thing we're going to take a look at here is, as far as electron domains, we'll say there's two locations according to this central atom where we could have two different locations electrons are found. Now, based on that, we don't really have a choice. It's linear, and we'll look again at an example here shortly. How many bonding pairs we're going to say that there are? We're going to say that there are two bonded pairs to other atoms, and there's 0 non-bonding pairs, lone pairs hanging out there doing nothing. And based on that, we'll say it's linear. So again, me just writing this down probably doesn't mean anything. Let me bounce over to another site, minimize this, and pull this up. This is the PHET site. So if you just did a Google search and said PHET and then did like molecular geometry, you could pull up this site here. So this is what I was just referring to. So if you take a look at your notes, we said that there was 2 electron domains, and here they are, 1 and 2. I'm not sure if my cursor is going to be visible or not when you actually look at this, but on the right side and left side of that purple structure thing, and based upon the non-bonding, here's the central atom, we're going to say there's none there. There's no non-bonded pairs. I could throw some in. Here's one pair and there's another one. But for the moment, we're going to say, nope, there aren't any. So based on this single central atom and 2 bonded pairs on there and no non-bonding pairs, the electron domain geometry is linear, and the molecular geometry is also linear, so it's a line. Now you may be saying, well, what if I only have 1 bonded pair? Well, every single time it's going to be linear. Well, what if you put it on a lone pair? It doesn't change. It's still linear. So we don't even mention that one. It's not really part of our discussion. But we can see that this is what it looks like in 3 dimensions. We can turn it around, which is pretty cool. This is a site a student told me about last year, and I love it, and I can't wait to use it again this year. Okay, so this is our first example, and this is it. There's no more other options. I am not going to change anything out or add electron pairs. It's just 2 electron domains. 1 on the left, 1 on the right, done. Okay, let's bounce back over to our notes. Blow this up. And we will do 3 electron domains. So if I have 3 locations in which electrons are found, period, I'm going to say that the shape is trigonal planar. And I'll put that below. Trigonal planar. And my first example will be 3 bonded pairs and 0 non-bonding pairs. So we're writing this down, then we'll use the model as a visual in just a moment. So if this is the case where it kind of just matches what we have over here, I'm just going to write that down again. It's the same thing. Trigonal planar. And I have another option. I can actually remove one of the bonded pairs and call it a non-bonded pair. And if that's the case, then we can either call it bent or angular. Either one works. So I'll just write that in here. Angular. All right, let's bounce over to the model site. Here we are. So we're back over here, and we said we're going to go with 3 electron domains. And so here it is. There's no non-bonding. We're just going to say they're all just 3 bonded pairs. And what's going on here is these electron pairs are negative, right? So they want to separate themselves as much as possible from each other. So you have this 120-degree angle thing. You should know that just based on your life experience in math class, that it's about 120 degrees between each of these pairs of electrons, so they can get as far away from each other as they can. And we can actually put that in here. Look at that, 120 degrees, perfect. Now, based on the shape, you can see down here, we already have written down, it's trigonoplanar and trigonoplanar, so we have that, perfect. Now, if we actually remove one of these and replace it with a lone pair of electrons, notice how it changes. So one of the things we should notice is, and I'll pull this up right here. They didn't really do it here. That's okay. This takes up more space than these. The lone pair of electrons takes more space than the bonded pair. This bonded pair, or either of these bonded pairs, are being held in a confined space between two positive nuclei. So it kind of makes their space smaller. In comparison to the lone pair, where they're floating a little more freely and they can go wherever they like. So here's our two examples of the trigonoplanar electron domains. And we have two different molecules we can look at. One was trigonoplanar and the other one was bent or angular. All right, we've got more examples coming in the next video.